All right, today we are doing 7.4 products in Algebra 2. Okay, so we're talking products again of radical numbers or radical expressions. So we're going to multiply radical expressions and multiply exponential expressions because those are kind of, again, two in the same thing, just two different ways to write them. So just a reminder, first step, okay, if we look at the radical expression, the number here is our index, so the n. We have the radical sign, and the number under the radical sign is the radicand. All right, we're going to use the product property to simplify radicals. Okay, it also allows us to simplify many products of radicals. So if we notice here that the radical, right, we have a radical sign, and they have the same index. Okay, if they have the same index, we can combine them. So this is the nth root of x times the nth root of y. We can just write that as the nth root of x times y. And that's what we're looking for. So if we have example 1, the square root of 6 times the square root of 8, that's equivalent to the square root of 6 times 8. We've kind of broken this down a couple different ways because you could do 48 and then do your prime factorization. You could go ahead and say, all right, well, 6 is 2 times 3. Break it into those. 8 is 2 times 2 times 2. Okay, and because it's a square root, you've got one group of 2, right? So we could pull out. And then you have another group of 2. So we could pull that out. And then the square, oh, I meant to write a radical sign. Then the 3 is going to stay under there, underneath that radical sign. So this is 4 times the square root of 3. Okay, and remember we can take these out because we have 2 of them. It's a square root, so we have to have 2 of them to have the square root. So 4 times the square root of 3 there. Here, in these, again, the term, the coefficient in front of the radical expression doesn't impact it to be able to combine them. So the 2 and the 5 are just going to go together. This is going to be 2 times 5. And then we have the cube root of each. So this is going to be the cube root of 4x squared times 16x. And then you could start breaking those down. This time we're looking for the cube root, right? So we need sets of 3. Here on the square root, we needed sets of 2. Now we need sets of 3 because we're looking for the cube root. So this is 10. And we're going to say times the cube root. And let's break these numbers down into their primes. So 4 is 2 times 2, or you could write 2 squared, times x, times 16 is going to be 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times x. All right, so we're looking for a cube root, so we need 3. So I have 1, 2, 3 2's, so I can bring that out. And I have 1, 2, 3, another group of 3's, so I can bring that another 2 out. And I have 1, 2, 3 x's, so I can bring an x out. And I already have a 10. And then I don't have anything else under my radical, so I'm just going to simplify this. 2 times 2 is 4. 4 times 10 is 40. And then I can't forget my x. So this, 2 times the cube root of 4x squared times 5 times the cube root of 16x is equal to 40x. Okay, that's our simplified answer. Okay, then let's look. The commutative, associative, and distributive properties hold true for complex numbers. The product property of radicals cannot be applied to negative radicands of even roots, however. Okay, so we've talked about this a little bit, perhaps. So if we have the square root of negative 1 times the square root of negative 1, that equals I times I, right? Because the square root of negative 1 is I, which is equal to I squared. And I squared is equal to negative 1. So we've talked about those negatives. But what we need to know is, therefore, we always express the square root of negative n, where n is greater than 0, as I times the square root of n when we're simplifying these expressions that contain square roots of negative numbers. So the key here is when it's a square root, okay? And we're just going to, instead of leaving the negative inside, we're going to bring the negative out as an I. Okay, so when example 2, it says simplify. So this one, it's a little tricky how you do it. I shouldn't say it's tricky. You have a couple options. You could go ahead and take the negative out because it's a negative, and that's what it said to do. So it could be I times the square root of 6 times I times the square root of 21. Or, like up here, you can see that the negative times, like whatever's under here is going to stay negative. But that can be a little confusing to remember, right? Because we have -1 times -1. It actually becomes, it stays -1 because we squared it, just like any other number. But it's harder to see when the numbers are different, I guess is my point. Anyway, all right, so this is going to simplify to I times I times the square root of 6 times 21. All right, so if we simplify, I times I is going to be I squared times the square root of 6 is 2 times 3 times 21. 21 is 3 times 7. Okay, so we're doing a square root, so we want a pair of numbers, so we have a 3. Okay, so I squared, remember, reduces to -1. Then we can pull out our 3, so times 3, times the square root of 2 times 7. And so that's going to be -1 times 3 is -3, our square root, and 2 times 7 is 14. There is our answer there. Okay, -3 times the square root of 14. And remember, I squared equals -1. Okay, always, always. Next, we're going to use the distributive property. So, use the distributive property to multiply radical expressions containing more than one term, and the FOIL method can be used to multiply radical expressions with 2 terms. Sorry, my paper wants to get crooked there with my setup. All right, so we're going to use the distributive property to multiply radicals with more than one term, and FOIL to multiply if they have more than 2 terms. So here we just need to distribute. We're going to take 2 times the square root of 3 and distribute it to each of the 3 terms inside here. So 2 times the square root of 3 times 1 is 2 times the square root of 3. 2 times the square root of 3 times the square root of 6. So we're going to do 2 times 3. And maybe I should write that out, but I'm not going to. So we're going to do 2 times 3. All right, and then our square root. So we have the square root of 3 times 6. Okay, so our first one is this. Then we're doing plus, sorry, that's a positive, not a multiplication, plus 2 times 3, and then the square root of 3 times the square root of 6. And then we have a minus, and we're going to distribute. 2 times the square root of 3 times 6 times the square root of 3. So 2 times 6, and then we have the square root of 3 times the square root of 3. I'll write it out like that. So I put each term in parentheses. So we ended up with 3 terms again. 2 times the square root of 3 is just going to stay there. Plus 2 times 3 is 6. And this is, we can reduce this, right, to be 3. 6 is going to be 2 times 3. Right, breaking that down into its primes. Minus 2 times 6 is 12. And then the square root of 3, I'm going to go ahead and check it here because we have 2 3's, so I can pull that 3 out and say, well, that's going to be times 3, and our square root is gone. So then I have 2 times the square root of 3 plus 6. Notice I have a pair of 3's in here, so I can take those out and leave the square root of 2 behind. And then minus 12 times 3 is 36. So then I've got 2 times the square root of 3 plus 6 times 3 is 18 times the square root of 2 minus 36. Okay, and I don't have like terms, right? This is the square root of 3, the square root of 2, and there's no square root. So I do not have like terms. I am finished there. I'm going to have to erase a little bit here. So let me take that out. All right, here I have two binomials, right? This is a binomial and this is a binomial. So this is when I have to FOIL. 5x times 2x. Well, 5 times 2 is 10. X times x is x squared. All right, then 5x times negative 3 times the square root of 2. So 5 times 3 is 15, and it's minus, right? Don't forget our minus sign, so it's going to be minus 15x. 5x times negative 3 is negative 15x, and then times the square root of 2. Okay, then, let's change up colors here. So FOIL, so now I'm going to go to the next set. Actually, it usually comes underneath how I usually draw it, but the square root of 2 times 2x is going to give me a positive 2x times the square root of 2. And the square root of 2 times negative 3 times the square root of 2 is going to give me negative 3 times the square root of 2 times 2. All right, then I have some like terms here, right? They both have a square root of 2, which means we have like terms. So 10x squared, so negative 15x, the square root of 2, plus 2x, the square root of 2. So negative 15 plus 2 is going to be negative 13x square root of 2 minus, okay, we've got minus 3, the square root of 2 times 2. Well, I have a group of 2's, so I can pull those out. So it's going to be 3 times 2, which is 6. And I don't have any more like terms, so I am done. Okay, our last one to FOIL, because we have two binomials. Okay, 1 minus the quantity 1 minus 3i times the quantity 2 minus 5i. So 1 times 2 is 2. 1 times negative 5i is negative 5i. Negative 3i times 2. Negative 3 times 2 is negative 6i. Negative 3i times negative 5i. Negative times a negative is a positive. 3 times 5 is 15. I times I is I squared. All right, then we have like terms. Negative 5i minus 6i. So I'm going to have 2. Negative 5i minus 6i is negative 11i. Plus 15i squared, remember, equals negative 1. So this is going to be plus 15 times negative 1, which is going to give us 2 minus 11i minus 15. I have like terms here, 2 and negative 15. So 2 minus 15 is going to give me negative 13 minus 11i. So it doesn't matter if we have radicals, if we have imaginary numbers, whatever. The same principles that we've been using, the distributive property, FOILing, I squared equals negative 1, the square root of negative 1 equals I. All of those things are coming back into play. We haven't ever lost them. All right, one more thing back here. The properties of exponents can be used to simplify exponential expressions with the same base or radicals with different indexes and the same radicand. Okay, so let's look at our first example here. It says 2 to the 7th times 32 to the x power. All right, so here's the thing. In order to multiply, right, exponential expressions, they need to have the same base. So can we get 32 to have a base of 2? All right, so let's do our prime factorization of 32. Okay, 32 divided by 2 is 16. divided by 2 is 8, divided by 2 is 4, divided by 2 is 2. So 32 is equal to 2 to the 1, 2, 3, 4, 5. So this would be 2 to the 7th times the quantity 2 to the 5th to the power of x. Does that make sense? Okay. Now, we know when we multiply, when we have the same base, and we're multiplying them, we just add our exponents. So we focus on our exponents. So we have 2. Well, let me back up. Maybe it would be better if I put this other step first. Okay, so let's go here. When we have a power raised to a power, we know that we multiply these. So this is 2 to the 7th times 2 to the 5x power. Because again, when we have a power raised to a power, we're just multiplying them. So then, let's do the next part. So when I have multiplication here and I have the same bases, I add the exponents. So this is going to be 2 to the 7 plus 5x power. These are not like terms, so I'm done. It doesn't look done, I know, right? I feel like it's very unfinished having this binomial here, but it actually is finished. Okay, so we have to remember all of those properties of exponents. Okay, so when we have a power to a power, we multiply them. When we're multiplying powers, we just add them. So we're going to use those rules. All right, so here we have the square root of 3 times the cube root of 9. It's kind of the same thing as the exponential notation. Okay, here we have to have the same radical, or the same radicand. No, the same index. Pardon me. Yikes. So they have to have the same index. So this one's 3, and this one is the 2. We never write it, so we assume it's a 2. We can't do anything because they need the same base in order to multiply. So we can think about, well, can we put them into exponential notation and get the same base? Or because we don't have the same index, so we can't do anything here. All right, so let's convert these to exponential notation. So this is 3 to the power of 1, right? We never write the 1. And it's a square root, so over 2. Awesome. And this is times 9 to the power of 1 over 3, because our index is 3. Okay. So again, we have the base here is not 3, the base here is 9. We have to have the same bases in order to multiply. So can we rewrite 9 with a base of 3? So if I look at the prime factorization of 9, I do 9 divided by 3, I get 3. So we can replace this 9 as 3 squared to the 1/3 power. And then it's being multiplied by 3 to the 1/2 power. Okay, so just like we did here, we're gonna, right, we did the power to the power. We're gonna do the same thing here. So this is the power to the power. So this is gonna be 3 to the 1/2 times 3, 2 times 1/3. We do 2 times 1 is 2. And if we wrote this as a fraction, 1 times 3 is 3. Awesome, so now we have 3 to the 1/2 power plus 3 to the 2/3 power. Now that we have the same base of 3 and they're being multiplied, we're going to add the exponents. So we're going to have 3 to the 1/2 plus the 2/3 power. Okay, which this doesn't look much different than this version, except here we didn't have like terms. 7 plus 5x. 7 and 5x are not like terms. Here, we can't add them because we have fractions, and to add fractions, we have to have the same denominator. So we're going to have to get the same denominator to add, just like we do in adding any other fraction. Okay, so I'm going to multiply this one by 2 over 2, and I'm going to multiply this one by 3 over 3. So I'm going to have 3 to the power of 3/6 plus 2 times 2 is 4/6. So 3 to the power of 3/6 plus 4/6 So my base is 3. 3 6 plus 4 6 is 7 6. Okay. So this could be our answer. The only thing is they gave it to us in radical form. So we could also put that back into radical form, right? So in radical form, that would be equal to the 6th root of 3 to the 7th power. Hey, the 7 is bigger than the 6, right? So we can actually simplify. I can take out 6 of these, right? Because I want 6, so this would cancel, and our radical would cancel, and I would have 1 left over in here. So this would equal the 6th root of 3 on the inside to the power of 1, and I would have a 3 out here. Hopefully that makes sense the way I described that. Okay, because this would be 3 to the power of 7 would be 1, 2, 3, 4, 5, 6, 7. A group of 6, so I shouldn't say the whole thing would cancel. A group of 6 can be pulled out. So maybe I should not have said that they would have canceled, because we still need to keep that. It's just we would only had 1 more 3 left afterwards. So 3 to the 6th times the 6th root of 3 is our answer there. Okay, so there is 7.4 for you, and I will see you later. Have a great one.